In the last few lectures, we defined the notion of an infinite sequence, which is an infinite ordered list of numbers. We are now ready to talk about infinite series, which are not the same thing, so be careful not to mix up the terms sequences and series. An infinite series is a sum. We denote this with this capital sigma notation. So sigma means sum, and then you have a lower index and an upper index. We are interested in infinite series, so the upper index is often infinity to mean go on forever. You want to add up terms that look like terms from the list that we studied when we studied sequences, but what we're going to do with those terms is we're going to add them. So we start with the lower index. In this case, it's n equals 1, but that's not obligatory. It could be n equals 0. That's pretty common. It could be n equals 2. Wherever you start, that's the first term in your sum. You add to that the second term in your sum, then the third term in your sum, and you keep adding terms until you get to this upper index. Now, it's possible that that is a finite number, in which case I would add up until something. But for an infinite series, it's infinity, and we just write dot, dot, dot to mean, hey, add these up forever. So in this lecture, we're going to look at a few examples of infinite series, and then over the next few lectures, we will talk about how to recognize when the sum actually exists, meaning it adds up to a finite number, versus when are we adding up something which perhaps if we added up forever would just get larger and larger and larger. Every single number can be presented as a series. Let me give you a few examples. Take the number 1/4, or 0.25. Using the base 10 decimal expansion for this number, which is just 0.25, I could say that this number is 2 over 10 plus 5 over 100. I could stop there, but I could also make it look like an infinite series where I say, and every other term is 0. Okay, so that's the number 1/4 presented in a way that makes it look like an infinite series. Let's take the number pi. Pi, 3.1415, that's as far as I can go. We could write this as 3 plus 1 over 10 plus 4 over 100 plus, assuming I'm right about 1415, it would be 1 over 1,000 plus 5 over, let me write 10,000 as 10 to the fourth power. And then we could keep going with the decimal expansion of pi, where every term in the decimal gets its own kind of base 10 fraction, if you will. So the next term would be whatever comes after 5 divided by 10 to the fifth. The problem with pi is that we don't have a pattern here, right? So let's look at a number where we do have a pattern. How about 0.3? 0.3 repeating. Okay, if I take the number 0.3333, et cetera, I could write this as 3 over 10 plus 3 over 100 plus 3 over 1,000 plus, we keep going like that. But this example is nice because I'm going to give you a closed form expression for the infinite series so that this whole expansion can be condensed into one nice sigma notation. This is the infinite sum from n equals 1 to infinity of 3 over 10 to the n. Let's verify I've done this correctly. So let me now start with this and kind of expand it out. When n equals 1, that's where we're going to start the summation. We have 3 over 10. When n equals 2, so then we go on to the next term. When n equals 2, we're looking at 3 over 10 to the 2. Or in other words, 3 over 100. Then we'd be looking at 3 over 10 cubed, etc. So indeed, this condensed form represents this infinite series all in one nice, concise notation. This is also an example where we can look at this and tell you what it adds up to. Okay, it adds up to 0.3 repeating, but let me give it another expression, 1/3. Okay, so this final example is more like the types of infinite series that we're going to be interested in. We're going to look at infinite series where we have a pattern. We can write down an expression here that tells us how to expand out every single number in our series. That's something that we couldn't do for pi because there is no formula. And it's also something that we wouldn't really want to do for 0.25 up here because almost everything was 0. Okay. This is actually a particular type of series that we will look at called a geometric series. This is a famous type of series that we will study. We won't study it any further in this lesson, but we will later. And what we are going to be interested in with this kind of series expressions in general, where we're looking at this form, is can we add it up to a number? In this case, the answer was 1/3. So can we do that? Or perhaps if we start trying to add together what this series gives us, we can't say that it adds up to anything. Maybe it adds up to infinity, or it just doesn't hone in on any one particular number. Let us now formally define what it means to say that an infinite series converges or diverges, meaning does not converge. To discuss the convergence of an infinite series, we actually pass to a sequence. We define a sequence called the sequence of partial sums. What these look like are truncated sums where instead of doing the infinite series, we only add up a certain amount. So the kth partial sum would be to add up the first k terms in this series. So what that would look like is I'm going to start with the first term, add to it the second term, and I'm going to keep adding until I get to the kth term. So this is a finite sum. It doesn't go on forever, which means it always exists. This is just a sum. It could be a sum of 17 numbers. It could be 2,000 numbers, but we can add up these numbers. They add up to something. So this always exists. From this, we generate a sequence of partial sums. The sequence looks like the first partial sum, the second partial sum, the third partial sum, and we keep going. So this is an infinite ordered list of numbers. It's a sequence, and each term in the sequence represents a partial sum. If the sequence is tending to a number, then we say, hey, the infinite sum is tending to that number. That's what it means for an infinite series to converge. So we look at the sequence and we say, does the sequence of partial sums converge? If it does, the series converges. If, on the other hand, this sequence of partial sums does not converge, because perhaps it grows to infinity or shrinks to negative infinity, or it bounces back and forth between numbers, something like that, then the infinite series does not converge. We say that it diverges. So let's analyze this infinite series where the terms look like 1 divided by the quantity n squared plus n. N starts at 1 and goes off to infinity. What I'm going to do is solve this two different ways. The first way, we'll just engage in some pattern recognition, and then I will show you an algebra trick that you might be able to use whenever you're looking at a rational expression like this, especially one where the denominator factors. Let's start with the first way, which is just to start cranking out what the partial sums look like and see if you can figure out if the limit of the partial sums exist. So what is the first partial sum? That's going to be the first term in this infinite series, which is 1 divided by 1 squared plus 1. So it's 1 divided by 1 squared plus 1, or in other words, it's 1 over 2, 1/2. The second partial sum is the sum of the first two terms. So that's 1/2 plus 1 divided by 2 squared plus 2. So I plug in n equals 2 into that denominator. So that's going to be 1/2 plus 1/6, which is 3/6 plus 1/6 is 4/6, which is 2/3. Okay. Let's proceed on to the third partial sum, s sub 3. I will write out all three terms and then I'll show you a shortcut with s sub 4. So s sub 3 is going to be 1/2 plus 1 over 6 plus 1 over 3 squared plus 3. So how about 9 plus 3, which is 1/12? Okay, I'm going to convert all these to a common denominator so I can actually add them together. So this is going to be 12. So 6 over 12 plus 2 over 12 plus 1 over 12 is 9 over 12, which divide everything by 3 is 3/4. Okay. Let me write one more, and then we will write down a general pattern, which you may be spotting as I continue to write these partial sums. If we go on to S sub 4, I'm going to add up the first three terms and then add to that the fourth term. Adding up to the first three terms is something I already did on the line just above. So S sub 4 I could think of as S sub 3 plus 1 over 4 squared plus 4. So that's going to be 3/4. I don't need to do this addition again. 3/4 plus 1 over 20. So that is 15/4 or 15/20 rather. Always fun to practice fractions, which is 16/20. Which divide everything by 4 is 4/5. Okay, that probably didn't surprise you. If you look at these partial sums now, they have a pattern. Recognizing patterns is critical to succeeding with infinite series in a calculus class. So sometimes you're looking at something and you've got to be able to spot that there's a pattern happening. We have a half, 2/3, 3/4, 4/5. The numerator matches the subscript on the partial sum. So if I look at this subscript, it's what I have here. This subscript is what I have here. This subscript and this subscript are the numerators I have here and here. The denominator is just one higher. So through pattern spotting, we can say that the nth partial sum is n divided by n plus 1. All right, so now I can tell you that the 200th partial sum is 200 divided by 201. The question we want to answer is, does this sequence of partial sums, so if I view this as a sequence, like that, my curly brackets are a little all over the place, but I'm trying to denote this as a sequence. Does this sequence converge to a finite number? If it does, that's what our series adds up to. In this case, we're looking at a rational expression with n. So we have n to the 1 divided by n to the 1 plus 1. This limit is going to be the ratio of the coefficients of the n terms. We have n to the 1 divided by n to the 1. So we look at this ratio and say that this sequence converges to the number 1. Therefore, the limit of our infinite series exists, or in other words, our infinite series converges, and it converges to the number 1. Okay, so we've already solved this problem. I'm going to step aside for a second and let you finish copying this down. I would like to come back and solve this another way, because the second way that we solve it is going to be a technique that generalizes to similar expressions where you have a denominator that factors. It may or may not work. So I'm going to give you a technique that you can try. We just showed, looking at the sequence of partial sums, that this infinite series converges to the number 1. But I'd like to solve this another way, because this is a technique that you may encounter if you recognize that you have a denominator kind of similar to this one. What I'm going to do is take this rational expression written in terms of n, and I'm going to break it apart into two expressions using partial fractions. So in particular, notice that 1 over n squared plus n is 1 over n times n plus 1. I'm not going to do a whole partial fraction decomposition here because we have a different lesson on that. That's not really the point of this exercise. But this would break apart into 1 over n minus 1 over n minus, or n plus 1. You can check if you add these together, you would have n plus 1 in this numerator and n in this numerator after you do the common denominator. So it would be n plus 1 minus n. That leaves you with 1. Given this way of writing the terms that we're adding together in this infinite series, let's list out the partial sums again. They're the same partial sums, but they're going to look a little bit different with this presentation. So S sub 1 is going to be the first term. So now I'm looking at this version of 1 over n squared plus n. So S sub 1 is 1 over 1 minus 1 over 2. It's a half. That's what we saw before. But now I'm looking at this as 1 minus 1 over 2. S sub 2 is going to be 1, I'm going to write out this, 1 minus 1 over 2. That's the first term. Now let's add to this the second term to form the second partial sum. That's going to be 1 over 2 minus 1 over 3. What I would like for you to see here is that the negative 1/2 cancels with the 1/2, leaving us with just two expressions, 1 minus 1/3, which is 3/3 minus a third, so that's 2/3. And that is what we saw before. Now let's write out S sub 3, and then we'll allow ourselves to generalize. So S sub 3 is going to be this plus this. I'm going to continue to write those terms as they are. So 1 minus 1 minus 1 half plus 1 half minus 1 third. Here's the new stuff, plus 1 third minus 1 fourth. Okay, take a look at that. What you might see, hopefully do see, is that all the interior expressions cancel out. So we've got minus a half, minus a third, plus a third. That leaves us with just the first term and the last term, as it did on the line above. So we have 1 minus 1 fourth, which returns us what we already found, which was 3 fourths. In the previous version of solving this problem, we focused on this final number and came up with a closed form expression for that. In this example, what I want us to focus on is really the expansion with all this cancellation leaving us with the first term and the last term. So given that emphasis, let's write down the nth partial sum. I'm going to imagine that n is larger than 3, so we've kind of gone out in our sequence. The nth partial sum in the sequence of partial sums, it would start the same way. It would be 1 minus a half, plus a half minus a third, plus a third minus a fourth, plus keep going until you get to what's new in this partial sum. And that's what happens with this index. So we would be adding to it 1 over n minus 1 over n minus n plus 1. There we go. So this is what's new for this partial sum, 1 over n minus 1 over n plus 1. Again, with our pattern recognition, we know what's going to happen here. All of the interior terms cancel. We see that literally with the first few. Then we trust this negative 1 fourth will cancel with a positive 1 fourth. And then there's going to be a negative 1 over n from the previous term that cancels with this 1 over n. And that leaves us with just two things, 1 and a negative 1 over n plus 1. So this is another way of presenting the sequence of partial sums. Sorry, I didn't write that very well. Sequence of partial sums. Here, it's very easy to take the limit as n goes to infinity. This term goes to 0, and just like before, the sequence of partial sums converges to 1. This kind of behavior where you have this kind of magic cancellation happening, this happens sometimes with similar looking series. This is called a telescoping sum. So if you have an expression which is similar, like a quadratic denominator typically, that you could break apart with partial fractions, if you write out the first few partial sums and you see this cancellation happening, you might be looking at a telescoping sum, which can give you two pieces of information. One, that the series converges, and two, what it actually converges to. We haven't had a chance yet to talk about the fact that sometimes you can know a series converges without actually being able to figure out what the sum is, so that we could say that the sum of the series not only exists but equals a number 1 is pretty special. Let's wrap up this lesson on series by looking at 3 examples of divergent series. So the first one is asking us to add up numbers of the form n from n equals 1 to infinity. So if I start to write out this just as an infinite series, if we expand this, it's going to look like 1, that's the first term, plus the second term, plus the third term, plus the fourth term. And this sum grows without bound. It does not add up to a finite number. So this series diverges. If a series converges, that means it adds up to a finite number. So you might be thinking, hey, this is going to infinity or something like that. This series diverges. It just diverges. Similarly, the second series diverges. We are being asked to add up 1 from n equals 1 to infinity. That looks like 1, that's the first term. And then the second term is also 1. And then the third term is also 1. And the fourth term is also 1. So this series diverges. It also gets arbitrarily large. It grows without bound. The third series is different. This one does not grow without bound. What we have here is negative 1 to the n. Notice here I'm starting with a lower index of n equals 0, which is totally fine. So your lower index, sometimes it's n equals 0, sometimes it's n equals 1, n equals 2. Just pay attention. It does not affect convergence or divergence. It just affects how you start your series computation. So negative 1 to the 0 is positive 1, but negative 1 to the 1 is negative 1. So my first two terms are 1 and then -1, but then +1 again, and then -1 again. This diverges. If you don't see that right away, why divergence is what's happening here, think about the sequence of partial sums. The sequence of partial sums, in this case, is going to look like 1 as the first partial sum. And then the second partial sum is the sum of the first two numbers, so that's 1 minus 1, 0. And then the third partial sum is 1 minus 1 plus 1, so it's 1 again, and then 0, and then 1, and then 0. This sequence does not converge to a number, so this sequence diverges. Let me just state what the partial sums are for the first two examples. This partial sum sequence, if you write it down, you can give a closed form expression using what's called the sum of consecutive integers formula. So the first one is 1, and then 1 plus 2, and then 1 plus 2 plus 3, and then 1 plus 3 plus 1 plus 2 plus 3 plus 4. Those are consecutive integers. There's a formula for that. It looks like n times n plus 1 divided by 2. This one, the sequence of partial sums, is 1, then 2, then 3, then 4. So this one is the sequence n. So both of these sequences grow without bounds, neither converges. Okay, so that was our first look at infinite series, but we will have many more lessons about infinite series.